Welcome to our presentation. Basically, it's direct transfer trip for anti-islanding with private LTE. My name is Tom Schwartz. I work for GE Vernova in our critical infrastructure communications business. And I guess I'll intro Brian. Your name is first, so I'll intro you. RFL Hubbell. I don't know. Do you want to say anything?
Just product manager, RFL Protection Communication Products. Want to introduce yourself?
Sure, and then I'm Nathan Irvin with NovaTech and product manager over our networking product line.
Good morning, everyone. My name is Kevin Lenehan. I'm an end-to-end solution architect for mission critical networks at Ericsson. Back to Tom.
So I'm going to hand it over to Brian for Hubbell.
Okay, see if these. All right, so as Tom said, our application here is centered around direct transfer trip for distributed energy resources and over using private cellular. So I'm going to start off with some little bit overview of power system islanding and direct transfer trip just to center us on the application. So a power system island is something that can happen when a generator, like a distributed energy resource, gets disconnected from the grid and continues to power a portion of the grid that it's connected to. So it can still continue to power utility customers, but it's disconnected from the larger portion of the grid. And this presents some challenges or some risks, and we break them down typically into three categories: personal safety, power quality, and equipment damage. So personal safety would be an issue, for example, if the generator's backfeeding power onto disconnected transmission or distribution lines. This could present a safety risk to utility personnel. It could be a safety risk to the general public as well, if you have down conductors, for example. So we want to be able to prevent that from happening. Also, power quality can be an issue. Without the regulation from the grid, there can be power fluctuations, and that can also cause equipment damage as a result, especially for sensitive loads that are connected to that island. So in general, for distributed energy resources that are of some larger magnitude, utilities will often require something to prevent that from happening. And often for these larger type of distributed energy resources, they will use a communication-assisted method for anti-islanding, and one of the most common methods for that is direct transfer trip. So basically, direct transfer trip is pretty simple in operation. When you have a substation breaker open, or if you have a line recloser open and lock out, it will send a signal based on that breaker or recloser position and send that signal to the generator and force it to not export any power anymore. And that's called a direct transfer trip signal. Typically, we use teleprotection equipment for that over various types of communication channels, and we send that direct transfer trip signal to the generator, and then it can disconnect and prevent export to the grid that it's still connected to if it was an island situation. As with any teleprotection channel, these are the three performance characteristics, reliability performance characteristics that you would typically measure. And those are security, dependability, and latency. Security being not cyber security, but that being the ability to not false operate in the presence of data corruption or noise on the communications channel. And dependability being the ability to operate when you actually want it to. When you receive that actual, or when you're sending that direct transfer trip, is it actually received and does it do the job that it's supposed to do? And we would call that dependability. And then finally, you have latency. This needs to operate in a certain amount of time. So we measure that in latency, end-to-end time, how long it takes to get that direct transfer trip signal from point A to point B. And so as part of this testing that we did, we measured these performance characteristics because it's critical to the operation of this type of application. So why cellular communications? Typically, in the past, There's a lot of legacy communication mediums that were used for direct transfer trip or for this application. These could be like leased telco circuits, even phone lines at one point, also T1 lines, for example. A lot of these are no longer available or being sunsetted, end-of-lifed by the telcos. So this presents a problem to utilities. How are they going to maintain these communication circuits? Also, if you still are using some of these legacy communication circuits, reliability is a major concern right now as the telcos kind of step away from these older legacy technologies. And the cost. A lot of times the cost is too high, and it actually can cause some generation projects to be unfeasible just due to the cost. You can't get a return on the investment quick enough. Direct fiber is always an option, but also very costly, especially over distance. So that kind of opens the door, opens the need for other kind of communication mediums for this type of application. Cellular is an attractive option, especially public cellular from a cost perspective. But then with private cellular, obviously you have additional benefits because the utility owns that network end to end. Also, security, from a cybersecurity perspective, owning that network end to end is a benefit for private cellular. And then also part of our testing, we wanted to have a redundancy use case here as well. So we utilized PRP, or Parallel Redundancy Protocol, over two networks, CBRS and Anterix. And what this allows you to have is two simultaneous direct transfer trip signals and communications end-to-end over two different paths, two different carriers. And with PRP, the first packet's going to win. So you're simultaneously sending data over two carriers, and you can receive that data simultaneously. If one circuit goes down or one band goes down, you still have the second band to receive that direct transfer trip. So you have seamless failover if one of those circuits goes down. So now I'll hand it back over to Tom.
Thanks, Brian. Just to add to what Brian was talking about with in this example, it was a mix of CBRS and Anterix. That could be Anterix and fiber. It could be Anterix and Ethernet. It could be Anterix with a public, like a Verizon, AT&T, T-Mobile. Really you can it's very flexible in what that backup is. It could be CBRS with fiber. You can really mix and match the technologies, but I think PRP in this case, like you said, is really important for that seamless failover. A traditional failover setup would typically be, kind of have some latent, discovery time that there was an issue, and then the failover time. This can take minutes sometimes, whereas in this case, it's the failover is instantaneous and seamless, which we'll show in the results, towards the end here. So I just wanted to do a quick introduction. I'm not going to go through all these bullet points, just on the equipment that we were using for this testing. So, and then, Kevin will get into his side and all that. At the edge, what we were using here is the GE MDS Orbit, line, or the GE Vernova, Orbit line. Basically, we used the MCR model that's there, where it has multiple wireless technologies. So in this case, like Brian was talking about, where we had Anterix and CBRS on at the same time, so simultaneous, dual cell capability. That's done in, actually this is a dual MCR right here, so active-active modems basically, that's what we're talking about. If we drill in a little bit further, really the equipment is capable of actually having a third SIM, so if we wanted to really get carried away on the redundancy, we could. So you could have not only seamless failover, but then also within one of those cards, a secondary, SIM card. So you'd end up with 3 SIMs in the unit in that case. So there's a lot of, flexibility from that perspective. And I guess, from the edge equipment, everything, connected up to the Ericsson equipment just fine. We did all the interrupt testing, which is nothing new. I mean, this is our 4th Plugfest now. And so that part of it's all well vetted, the interoperability piece. So what we're doing here is just, now we're working on real applications. And, I'll hand it off to Kevin to introduce his equipment and what we did in the lab.
Thanks, Tom. Yeah, so I'm going to describe the Plugfest architecture we set up in what we call our Utilities Innovation Center, or UIC. You know, and Ericsson had the privilege of working with 3 of the 6 use case teams. So 2 of the teams came into our Utilities Innovation Center, and then one of the teams we actually set up a network at their utility lab. So this is the architecture of what we had in the UIC. So we have an on-prem private network in the UIC room. We have the core there. It's a single server core. And then we had an existing eNode B indoors broadcasting CBRS and Anterix Band 106. So for Plugfest, we added a second eNode B, about 200 yards outdoors on our parking garage roof. We are broadcasting the 2 bands, CBRS and Band 8, and we made it look like 2 networks by broadcasting 2 network IDs or PLMN IDs. And that really allowed, you know, the use of 2 SIM cards and then that PRP feature to go. Is that, what do you see in there? Okay, I want to talk about the way the packets were traveling through the network. And this is, what we're showing here is from the UE out through the core to the cloud, to, you know, and to the internet. That's typically kind of what works with your smartphone, or in the case of our setup here, to some of the head-end applications, the device management. And the latency here is typically about 50 or 60 milliseconds for those packets to travel out to the application and back. But we have set up in this situation to lower the latency is what we call UE to UE routing. And you know, that's really can be done on all the utility networks. It's a way to really lower the latency. And you can see here the packets are traveling from one router through the eNode B, through the core, never leaves the site, and then to the other eNode B and to the other router. And that lowers the latency quite a bit. So from a ping-to-ping standpoint, the latency we were seeing was about 35 milliseconds. And that's about half of what you get going out to the internet and back. So, you know, you can look at that concept. You don't need an individual private network. You can sort of set up this, well, you can set up this architecture, which what's called a local packet gateway. So you have the packet gateway is a core function in that big utility core, you know, serving multiple states. But you can bring a second packet gateway, a local packet gateway, and move it towards the edge and do the packet processing there. So that could be like near a cluster of eNode Bs, for example, or you can move it on-prem, say in a power plant. And the advantage there is, of course, the low latency and the low latency use cases. And you know, in a power plant, it might be a robot. The other advantage is you can do your edge compute right there at the local packet gateway. And so lowering the latency on the application layer, and from a security standpoint, it's ideal because those packets never travel out on the internet where they could be intercepted. So with that, Tom's gonna talk about one of the detailed architecture slide, and then I'm gonna show you some images of the actual gear we set up.
Awesome, thanks, Kevin. Yeah, so now we're going to kind of move into, you know, the DTT anti-islanding, you know, over private LTE, you know, kind of test setup and results, like Kevin said. So in this image here, you know, I tried to kind of simplify it down so that we had, you know, kind of like what Brian was saying earlier. You know, really, you've got some distributed energy resource. So, you know, I'm from upstate New York, for example. So almost every single town where I live now has a pretty big solar farm in it somewhere. You need to be able to remotely disconnect that generation from the grid for the multiple reasons that you were talking about, right? Safety, fire prevention, equipment, failure prevention, things like that. So if we had kind of a hypothetical remote location, with some generation there that we wanted to disconnect, we'd be using, in this case, you've got the Ericsson core and the RAN, you've got the GE Orbit, edge routers, and then you've got the Guard 8000 as kind of the DTT. I believe it was Goose message based, right? So you've got your 61850 traffic going, and then we've got the NovaTech equipment, which Nathan here will get into, what that box does and really why that was in place from a SCADA perspective. And really what we're doing here is we are, like I said, it's active cellular, and we're using a GRE tunnel. The reason you need to use a GRE tunnel is because cellular typically operates at kind of layer 3, right? Just like the internet. So you're sending things to IP addresses. Unfortunately, Goose messaging is a layer 2 protocol. So how do you get that traffic to cross the cellular network, being a layer 2 protocol? So that's what GRE tunnels come into play for. What we're going to do is we're going to package that layer 2 message into a layer 3 message, send it to the other side, unpackage it, and now your layer 2 message just basically went along for the ride. The other thing you mentioned earlier was security, right? And not just security. I know that term can be interchanged, right? So the cybersecurity guy would say, oh, that's just prevent eavesdropping and man-of-the-middle attacks and things like that. But security also means it's almost reliability, right? Like verification that you have no false trips and things like that. In this case, when I talk security, I mean AES 256, IPsec VPN connection. In your case, your security, messaging was really the PRP side, right? Is making sure that, that the messaging is getting there and we're not having any failures. We also ended up using VRF, the protocol VRF. So what that's for is we ended up configuring on the orbits, one Ethernet port was dedicated for CBRS, the other Ethernet port was dedicated for the enteric side. So some of those advanced networking features that you may not have come across or thought about in the past, they really come in handy for situations like this, so you can kind of use this equipment for some of these more advanced cases to be able to transfer that Goose messaging in a quick and reliable and secure way. And then I guess I'll hand it back over to Kevin here. And he'll kind of go over the, kind of some images from testing and just kind of give you a little bit more visual aspect of what you were talking about earlier, right?
Thanks, Tom. So this is kind of a Google Earth view of what we set up here, that second eNode B. So I guess on your right, you see the core and the eNode B that's in the UIC. Did is we set up a second eNode B over on that parking garage roof there, and that was covering the UEs down there. You see over there in by those trees, and that's where we set up a cabinet, and we had all the second eNode B devices in there. So the traffic was traveling over that fiber backhaul from eNode B2 into the UIC to the core. So here we're seeing the test equipment we had indoors. So we have the GE Orbit router. You're looking at the Ericsson baseband there. Also our router. You're seeing the NovaTech SCADA gear, and then the Hubbell Guard 8000. This is a look indoor at the UIC network. So that's cabinet there, or that flight rack, has the core in it, the single server core, some of the NovaTech gear, our router, multi-purpose server, and then to the right of that, you're seeing the two radios. The big box there is a 2212. The smaller radio up is a CBRS small cell that we have an external antenna on. That's what you're seeing up top on that stand. You're seeing the CBRS antenna and the 800 megahertz antenna. And then we got a couple spectrum analyzers in there you can see. So on the left there, you see the Anterix spectrum. So that's we're looking at a 5 megahertz bandwidth across that entire screen, and so you're seeing the 3 megahertz downlink carrier. Over on and plenty of signal to noise. That's like easily 30 dB. And then on the right, you're seeing the CBRS band. So that scale is 150 megahertz across the bottom. And so you're seeing several 20 megahertz carriers in there. The SAS grants that spectrum. And all the way to the left, that's the actual 20 megahertz carrier that we were using for the traffic for this use case. And then this is just a look at the outdoor site, some details. So up there you see a radio farm. You can see in the middle pole, that's our 2 little antennas like you saw indoors. The middle picture is a back view from the cabinet. We had all the outdoor equipment in, looking up to where the eNode B was and the antennas on the roof. You can, to the right or to your left there, you can see all the external antennas that were hooked up to the router, and then you can see the gear inside the cabinet below, the Guard 8000 and the MDS orbit router. With that, I'm going to hand it over to Nathan from NovaTech.
Thanks, Kevin. Excuse me. So I'm actually going to jump past this slide and then I'll come back to it. I know you've seen a version of this particular slide, kind of the overall topology of the setup. But what we include here this is an actual HMI that's been generated with the drawing package on our Orion VX, which is our virtual RTU platform, kind of like a SCADA platform. So you're able to create these one lines and basically visualize your network topology, or whether it be other devices at a substation, you can include those as well. In this case, we've created this HMI to again visualize the success rate, and then I think Brian will probably get into the different buckets that we had after this, where we talk through some of the results. But basically, there's 3 elements from NovaTech on this: the Orion LX RTU, which was at kind of our mock substation side, and then we had an Orion MX RTU at our mock generation site, and then the Orion VX. So let me then jump ahead. Well, before I do, just to kind of talk about the different connections that we utilized for the Orions. So the VX platform was connected to the Ericsson core through DMP3 over the IPsec, so VPN in. So that was actually hosted in Lenexa, but then the VPN to the core itself. So then the LX on the generation side, we used DNP3 over IP, and that was a connection both to the Guard as well as the GE, the Orbit. So those connections were all Ethernet based, whereas on the generation site, we used a different connection to the Guard, which was actual hardwired relay. So if you had any other relays or devices, that's an example of how we can just capture the pulse count instead of DMP3 traffic directly. And then we use a converter to serial to go to the orbit on that side. And again, I went the wrong way. So there's kind of 3 different logic elements that we included on this to be able to capture the success rate and put together these counters. So in the Orion platform, there's different packages you can add, and one of them is Logic Pack. The reason that we have Logic Pack is for basic arithmetic and applications. It's basically to say that, you know, simple math doesn't need to be hard. So in this case, we were able to set up primary and secondary inputs for the substation side so that we could capture either the CBRS or the Anterix network and funnel those into a single bucket. So if one of those networks happen to go down, we have failover on that communication and be able to still get the data input. And it actually allows us to visualize then back on the Orion VX HMI, if a network goes down, we can actually capture that and display that within the diagram. We also then had simple logic that would determine the buckets, and again, which bucket or how long that trip from sent to received took, so that we could increase those counters and have and receive that data from the guard, and then we could again put those into that visualization. And then within the Orion VX, we actually applied a slightly more advanced, but using Lua scripting, and that's another package that you can add to be able to then calculate the overall success rate of the trips sent and received. All right, with that, I'll pass it back, I believe. I'm not sure who wanted to capture this one. You want to talk to this?
Sure. Yeah, so as I mentioned earlier, dependability is one of the critical performance characteristics of this type of system. So the way we did this was we actually measured the amount of time it takes to send a DTT signal from A to B, and then we actually hairpinned it and sent it back to A. That way we had a common time reference at A, and we could measure a complete round trip time. And then, you can divide that by 2 to understand what your one-way A to B time was. So nominally, we had around 80 milliseconds round trip, so 40 milliseconds. I think Kevin said about maybe 35 in some cases. But we really wanted to understand how that operated over time and repeatedly. And when you do dependability testing, you really want to not only verify that you actually received that signal, but you want to verify that you received it in a certain amount of time. So the way we did that is we repeatedly sent trip signals, one after the other. I think we sent 2 every second, for example. And then we measured that round trip time. And as Nathan was alluding to, we put them into different buckets, and we can calculate a percentage of how many of those trips were received within a certain amount of time. And this shows some of those results. For example, in this data set here, we sent like 11,876 trips being sent, and then you can see the different buckets there with the 3 bullets on the bottom. Within 60 milliseconds, keep in mind this is round trip times. Within 60 milliseconds, 75 milliseconds, and 150 milliseconds, and you can see the different percentages for those there.
Yeah, so then the other piece that Brian talked about earlier is really that resiliency, right, using PRP. The reason we do that is so that we can have that seamless failover. So what we did, after we got some good baseline numbers and we saw that we had 100% trip rate, no failures, then we started inducing failures into the network, right? So how do we test that failover, that seamless failover? So we tried a few different ways. We were disconnecting Ethernet ports, we were taking network equipment down, taking eNode Bs down, things like that, just trying to simulate some real world failures. And really with all of our testing that we did, if you had some fault on the enteric side, we took that down. It was there were 0 missed trips because we were still sending everything over the CBRS side. Same thing with once we brought it back up, we did a bunch of failures on the CBRS side, brought that down. Again, 0 missed trips, which makes sense, right? Because that's really why we're using PRP in this case. And then the other part is just really no receive alarms, no false trips. Really making sure that security is indeed there. Overall, I guess I might open this up a little bit to you guys. From our testing in general, I found that because Brian and I have done this testing before on public carriers with very similar equipment, and the latency was on the public carriers was about twice that of our testing, with the private network. The latencies were very good. I would say, and I don't know, Kevin, would you agree with this, that the enteric spectrum seem to have lower latency than that of CBRS with our testing?
I would agree with that. So I think the factor there is, CBRS is 3.5 gigahertz and it's TDD spectrum, and with 5G they speeded that all up. They put in something that's called a mini slot, and so at 5G, you'll see that TDD spectrum perform at a lower latency. So that was expected.
Thanks, Kevin. Yeah, overall, I was really impressed with the results. I think it definitely proves itself as a feasible application. I know you guys are already working on some real-world applications in the field, actually using our orbits as well. So it's going from lab tests to proven field applications at this point. So I'm really looking forward to kind of the future with this type of application, both on public LTE and private LTE moving forward, because I think it really is a good advantage. One thing that we didn't talk about was the potential of, because it's a private LTE system, we could apply, at the core, we could apply quality of service rules based on the application, and we could, some further testing we could, do in the future, maybe for next year, is apply, traffic flooding and things like that, and actually have, quality of service priorities at the core, so that we can show that even under stressful conditions on the network, that we can still get those trips across in the same or reasonable timeframes as well. So maybe a thought for the future. Yeah, go ahead, Kevin.
I just want to make one point about latency that's important to know. You really need to know what is the latency measurement. So, right, is it over-the-air latency, which is just the air interface? So typically with 5G, you're talking about 1 millisecond latency, that sort of thing. That's over the air with like millimeter wave. Now, you have the end-to-end latency at the network layer, so the ping we were talking about. And then when you go to the application layer, when you're actually doing some processing on top of it, some algorithms, then there's the application layer latency. So we were talking about two things here, right? We were talking about the network layer latency when I talked about 35 milliseconds, and then we were talking about the application layer latency, which is the last thing we talked about here, that measurement.
Yeah, thanks, Kevin, for bringing that up, because it does, if you don't know which layer we're talking about, it can almost look like we're talking two different latencies, right? Really, like I said, I think it's definitely a viable system. One thing too, just a baseline, since you were talking about latency, really when we're talking about substation to substation teleprotection, that's a different story, right? I mean, you're talking 5-6 milliseconds, spec usually. That's not what we're talking about here. This is distributed energy resources where the latency is a little less strict. So we're talking, a lot of the users we talk to, I don't know if you would agree with this, is typically the spec is 1 second. Is there a number that you've seen that's lower, or?
Usually utilities trying to get to prevent that island from forming in 2 seconds total, but that includes breaker operation time, communication time, any controls involved. So that's a total time. Generally speaking, from a communication point of view, 100 milliseconds for this type of application, would certainly be acceptable.
Yeah, that's really good information, because you don't want the comms piece being 1.9 seconds of that 2 seconds, because you're going to end up with damage or potential harm to people. So. So I guess with that, unless you guys have anything else to add, I'll give everybody a few minutes for questions. Yeah, go ahead. Yeah, I'll let Brian answer that. Yeah.
That's why we did the dependability testing. Oh, restate the. Okay, the question. Sorry if I don't get it exactly verbatim, but the question was about variation in latency and how did we test for that? Is that fair? Yeah. So that was the purpose of the dependability testing, and doing those continuous trips being sent and received. We did thousands and thousands of those, and being able to measure what percentage of those were received within 80 milliseconds, 100 milliseconds, 150 milliseconds, I think was our largest bucket. So that can characterize the amount of jitter or the change in latency over time. So we did that for hours, and then sending trips 2 every second, and then verifying how quickly they came in, and basically calculating a percentage of those received within certain time criteria. So that is how we tested the variation in latency. So we knew that, for example, 100% of the trips sent over a long period of time were received within 150 milliseconds, round trip, by the way, within 150 milliseconds. And I forget the exact numbers, but 99.9 were in 100 milliseconds, for example. I don't know if you can speak that. I mean, one thing I'll say is that, like was alluded to before, was that one of the networks was faster than the other, and because of the nature of PRP, whatever packet was received first, would win in that situation. So disruptions on one network probably wouldn't manifest itself in terms of the latency because of doing PRP. But I'll let Tom speak to some of the other testing.
Yeah, I mean, you bring up a good point, right? Because we did see a intrinsic higher latency CBRS network. So really, when both networks were up and happy, I'd say 99% of the time the Anterix network was winning in that case. It was getting there first. To your point, let's say there was some issue with the Anterix network, some delay or some failure. It doesn't really matter because CBRS is still there, but to your point, because there is a slight latency difference between the two networks, you would notice some jitter there because now you've got, where we were looking at, 60 milliseconds round trip, 70 milliseconds round trip. Now we might bump to 100 milliseconds round trip because now it's on CBRS. So it's actually, it's a very valid point. And one of the things that we do in our lab in Rochester when we're doing, kind of goose trip, DTT type testing is we'll actually graph the latency of every single trip over time using LabVIEW. So we'd be able to, maybe that would be another thing that we could do next year, if we continue this type of application is maybe we actually graph each individual data point and then we can actually get that jitter number, min, max, average, deviation, all that. So yeah, a good question. Okay. Any other questions? Thanks for showing up. Yeah, go ahead.
I could just elaborate a little on the last question. So, we could have, and maybe for next year, we could have loaded the traffic with the network with traffic, right? And then see what effect that had on the latency and this particular traffic. And so, what you do there, and you can handle that with quality of service, right? So you can provide different quality of service levels to different traffics and different IP addresses. So that'll prioritize that traffic over other traffic. So for example, this mission critical traffic would get priority from the scheduler over, say, AMI traffic, utility meter traffic. And so that it'll get the throughput grants sooner than any other traffic. So that's one way you can be assured you get the high reliability on a loaded network.
No, I'm glad you guys brought up these questions because I mean that's if we decide to expand on this for next year, those are some really good recommendations to take this another step further. Right? Is I'm looking at individual data points, latencies. That'd be a good suggestion, and then loading up the network and running quality of service and really proving why private LTE has some advantages over some of the public carriers in that case. So really good questions. I know we just got a minute left, so are there any other questions? All right. Well, I appreciate you guys coming out. I know this session was early, so 8 o'clock session, so we appreciate you coming out. If you have any questions afterwards, feel free to stop by any of our booths. And then we have another session. We'll be replaying this at 10 if you want to, if you got in here a little late. Thanks, guys.